Thanks for joining me to listen to the lecture on metallic bonding, so the chapter 2.4 in our course in solid state physics. And the take-home message of this lecture regarding metallic bonding is that we just honestly admit that the mathematical treatment that we would need to properly understand metallic bonding, it's really too complicated, so that we cannot really go into the mathematical details. So we just need to mention roughly what happens, and that's it. And later on, we will learn a little bit about metals and their conductivity, so electric conductivity and other properties, and that will be enough for metallic bonding and metals as such. So what happens in metals, and if we look of elemental solids, so solids formed out of elements only, so we look at the periodic table, we really see that most of elemental solids, they're actually metallic. So covalent bonds, they only take place nearby the group 14, and then we have ionic solids on the far edges, but otherwise, we don't really have that much of other bond types than metals. And what happens in these structures is that the valence electrons, they move freely between the ionic cores, and that's one of the defining properties of metals, and this is really the property feature of metals that really gives rise to many of its macroscopic properties. So please remember this. Valence electrons, they somehow form a electron gas, and then this electron gas and the free movements of electrons, that's what gives rise to the macroscopic properties. So for example, they participate on the thermal conductivity, and they participate on the electron conductivity of metals, and so forth. And subsequently, because it is these free electrons, these valence electrons that participate in the conduction of electricity, is that they are subsequently called conduction electrons. And this is a term you should remember if you already haven't done so. Detailed description, as I tried mentioning already in the beginning, is that it's quite involved, in fact. But in essence, we can at least understand the governing principles. So why metallic bonding happens is that it is energetically favorable. So what that's the kind of principle, physical principle that explains why this kind of bonding takes place. And energy is minimized, and that gives rise to metallic bonding being formed. And what we do here is that instead of trying to do any serious bits of mathematics, we'll just say for now that what are the things that play a role in the bonding formation, and we are happy about that. So happy with it. We don't need to go into the fuller details right now. So the kinetic energy is a thing that matters, and when we will have conduction electrons, the kinetic energy is minimized. This may sound a little bit obscure, because the conduction electrons are free, so they form a freely moving gas of electrons. But this starts making sense when we also remember that we have this uncertainty principle in place when we are dealing with quantum mechanical objects. And especially when we are thinking of the uncertainty principle between the position x and momentum p. So these are the conjugate variables, and these are associated with the uncertainty principle. And this then means that if we have a very freely moving electron, so that we don't really know where it is, then in this slang, it means that the x operator results in a very delocalized state. Then the uncertainty principle dictates to us that then the momentum should be quite localized. And this is the kind of reasoning that then tells us that in the end, the conduction electrons' kinetic energies gets minimized. They have quite localized momentum, and momentum is related to the kinetic energy, and it cannot have very high values, and that minimizes the kinetic energy contribution. Another consideration is the potential energy, and that is of course affected by the electrostatic forces. So we have an equilibrium position, electrostatic forces play a role, and of course the Pauli exclusion principle is another major contribution here. What we know by performing experiments and learning based on that is that the metallic bonding is favorable when we have closed packed structures. And what happens with closed packed structures is that they tend to maximize the overlap between the valence electron orbitals. The closer the atoms are to each other, to the adjacent atoms, the closer the electrons also are. And this is somehow important in formation of metallic bonds. Another thing that is being maximized when we have closed packed structures, such as the FCC and the hexagonal closest packed structures, HCP, is also the number of nearest neighbors. So these are the kind of considerations that then matter. That somehow it's favorable for a metal to form by just packing atoms close to each other, and somehow this packing then frees the electrons to move nearby and free matter in a gas-like manner. And this is the kind of then the property that then dictates the main macroscopic properties of metals. And let me remind you the good thermal conductivity, the good electrical conductivity of metals. That's one of their defining characteristics. And also in terms of the mechanical properties, and this is actually quite interesting, they're malleable, the metals. With that, I mean that they're not very brittle materials that we can actually hammer down a piece of a metal and it doesn't break. Instead, they start molding into different shapes. And this is a kind of macroscopic mechanical property that is associated with metals in general. And since we are dealing with periodic structures here, and we have been thinking of this periodic structure to be quite rigid, maybe we can grasp somehow in our minds that in this metallic bonding, it's really the conduction electrons, this conduction electron gas that is being formed, that has a major contribution to the minimization of energy. So even though we hammer down a piece of a crystalline metal, it can change its shape, but it doesn't break down, so that these valence electrons, these conduction electrons, somehow they stick them between pieces of polycrystalline together, so that we can actually mold metals on a macroscopic scale. And this is very different behavior. So for example, from covalent solids. We can imagine that we take a diamond or silicon and we start hammering it down. It doesn't mold. It doesn't change shape. That it fractures. It explodes into tiny bits and pieces. So that's what will happen with covalent solids. So these are the kind of things that hopefully after the end of the course we can start appreciating, that we have different materials, different kinds of solids, and hopefully we can also understand their properties arising from these microscopic principles. So that's the kind of main points that we want to teach you during this course. How can we understand macroscopic properties of solids based on their microscopic properties? So I will stop here regarding metallic bonding, and soon we will continue with hydrogen bonding. Thanks for listening and take care.